All right. Once again, welcome to MUBIT's webinar series on demystifying industrial AI. This webinar today is part of a larger three-part series. Back in November and December, we executed on parts 1 and part 2 of the series, which are now available on demand. We'll provide the link to those at the end of today's session and in the chat. Today's topic is part 3, a taxonomy of process optimization and control. A couple of housekeeping items for you before we get started with today's session. The session is being recorded, and the recording will be emailed to you after the fact. You are invited to submit questions during the presentation using the questions console on the bottom right-hand side of your screen. Note that if you use the chat, it's a little bit confusing for us, so please use the questions console. In specifically, the Q&A will follow the presentation, so we'll save those all till the end, and you're welcome to upvote questions that you like to get them more likely to be answered online. And then we'll use polls potentially throughout the presentation. So we'll get started really quick with a quick poll on what roles you all have in your organization so that Nadav has an idea of who we're talking to today. Alrighty, Nadav, it looks like you've got about 2/3 of the folks online that are in process controls, advanced process controls, or real-time optimization. A couple folks from the AI and data science world, some folks with others. So feel free, if you are answering other, to drop your role in the chat so we know a little bit more about you. Awesome. I appreciate you guys all for participating in that. And with that, we'll go ahead and hand it over to Nadav to get started with today's topic, demystifying industrial AI, a taxonomy of process control and optimization, from model predictive control to reinforcement learning.
Thank you, Allison. Thank you very much. I hope you can hear me well. Please let me know if there are technical issues along the way. And without further ado, let's get started in our third and final part of the series. So we will talk today about the taxonomy of process control and optimization, from model predictive control to reinforcement learning. Just a brief reminder about myself. I am co-founder, the president, and CTO of MUBIT. My area of expertise is the mathematical foundations of neural networks, which are the main driver behind modern AI. I'm a professor of computer science, education originally in electrical engineering, mathematics, and computer science. I received several recognitions for my contributions to the foundations of AI. Specifically, I was 4th person in the world to get a Google doctoral fellowship. And aside the academic background, I have about 2 decades of experience applying AI to industrial systems. And for the last close to 10 years now, it's been to the process industries. All right, so this is our plan for today. We're going to start by presenting the high-level problem of process control and optimization, and then start talking about different approaches to solve this problem, starting with a wide class of approaches known as model predictive control, and then continuing to reinforcement learning. So, process control and optimization. In process control and optimization, our goal is to steer some system to maximize some objective while respecting constraints. So we have a system and we have a controller, and the controller can drive manipulated variables which impact the system. Okay? So the system is impacted, and there are controlled variables which represent the state of the system. And these are impacted by the manipulated variables. There are also surroundings that drive disturbance variables. These impact the system but are not impacted by the system. So ambient temperature is an example of a disturbance variable. And usually the controller has access to some of the disturbance variables, and it could take those into account when it makes decisions on how to move manipulated variables. There is some objective function that's defined, and it could depend on manipulated, controlled, and disturbance variables, and also on different parameters that the user can set, like market prices or things like that. these parameters are typically accessible to the controller, and there are constraints, okay? Usually upper and lower bounds, and there's a constraints evaluation function that could depend on manipulated variables, controlled variables, and disturbance variables, and also on parameters that the controller could also see. So this process of setting manipulated variables and observing the controlled variables and these surroundings providing disturbance variables, that's a single iteration, and it repeats again and again and again. And the controller's goal in life is to maximize the objective while respecting the constraints. And a major challenge here, at least in real-world settings, is that the behavior of the system can be very, very complex. And it oftentimes is in real-world plants. An example of a system, this is from the world of refining and FCC, fluid catalytic cracking. Okay, so I'm not going to get into the details of the process. It has kind of three main areas: the reactor, regenerator, and the main fractionator. There are manipulated variables: heavy feed rate, total feed rate, and riser temperature. There are a number of controlled variables and a number of disturbance variables. And there's an objective function on the right, which depends on the different products that are produced. So the objective function is the sum of the product rates times their prices, minus the sum of the feed rates, which are manipulated variables, times their prices. Okay, so it's an economic objective. And the prices are parameters that can be set in real time. There are upper and lower bounds, constraints. Every MV, every manipulated variable, has both upper and lower bounds. And some of the controlled variables have upper and or lower bounds. Like flue gas CO has an upper and lower bound. The main fractionator overhead rate has an upper bound, and the olefins rate has an upper bound. Okay, so this is an example of a process control and optimization problem. And for those that are familiar with this process, you know that there are pretty substantial nonlinearities going on here. So the system is indeed complex. Now let's discuss model predictive control, starting with the abstract definition and then moving on to concrete examples. So in model predictive control, we have a model of the system, okay? And that model receives MVs, CVs, and DVs. I repeat, these are manipulated variables, controlled variables, and disturbance variables. Okay? So it receives them at every time step. The time here is discrete. Okay? So the model operates in discrete steps, like every minute, every 3 minutes, or something else. And given these variables at time t, the model predicts the controlled variables at the next time step. So you could have more elaborate models that receive a window in time, not just the current time step, but for simplicity, this is what we're going to focus on. The ideas are exactly the same. In model predictive control, the real-time control and optimization process works as follows. At every time step t, I set the manipulated variables, I set the MVs through a planning process that relies on the system model. What does that mean? I have my system model, and I send to it the controlled variables and the disturbance variables at the current time step from the true system and the surroundings. And then for a given value of manipulated variables at this time step, the system model will give me the controlled variables at the next time step. Then I feed into it the DVs at the next time step, the MVs at the next time step, and I will get the CVs at the time step that follows. I continue in this fashion for a predetermined number of steps. That number of steps is called the horizon. Okay. Then I have an objective function that depends on the MVs, CVs, and DVs throughout the horizon, and also on parameters. And I have constraints evaluation function that also depends on the MVs, CVs, and DVs throughout the horizon, and on constraints parameters. The disturbance variables are set through extrapolation. This could be simple extrapolation, such as assuming that the DVs will remain constant, or it could be more sophisticated extrapolation based on prediction. Any option qualifies here. And then the manipulated variables are set through a solver. That means that they are adjusted to maximize the objective while respecting the constraints. So I run a search process here of searching for the MV sequence that will give me the best results. And then I take the MVs at the current time step and I feed them to the true system. Okay? That's a step of real-time control and optimization with MPC, with Model Predictive Control. In terms of success criteria for MPC, so I'll give here a list of important criteria. It's not necessarily exhaustive, but these are the criteria that I believe are maybe the most important. First is that we want our model to have the capacity to capture the complexities of the true system. Second is that we want to be able to conduct real-time control and optimization in a computationally efficient way. That solver that I described in the previous slide, it could involve a significant computational toll, and we want that toll to be low enough so that we could do it in real time every step, like every minute or every few seconds. And thirdly, we want the control moves to be robust to model misidentification, because no matter how good my model is, it's always imperfect. It's always wrong sometimes. And I want the control moves to make sense, even though the model is not perfectly accurate. Okay, so now let's move on to discuss different types of MPC, of Model Predictive Control. And we'll start with the simplest and move our way up from there. And the simplest is linear MPC, linear Model Predictive Control. In linear MPC, the system model is linear. So the CVs at the next time step are a linear function of the CVs in the current time step, the MVs in the current time step, and the DVs in the current time step. And the coefficients of the linear function, which are matrices, these are parameters of the model. So the first matrix, that's the CV to CV gains. Second matrix is MV to CV gains. And third matrix is DV to CV gains. Running MPC with such models is something that's very widespread in the industry. In fact, this is the main engine behind advanced process control. In terms of the success criteria, then I'm arguing that the situation is roughly as follows. The ability to capture complex systems is fairly limited because by definition, the model cannot capture nonlinearities. It's linear. We will talk about other types of similar models that can capture nonlinearities, but this one, the one that I just presented, is purely linear. So by definition, it cannot capture nonlinear behaviors. Every real system is essentially nonlinear. Locally, systems might behave linearly. So if you want to solve local problems, that might suffice. But if you want to solve global optimization problems, then in the vast majority of cases, you will need to capture nonlinearity. In terms of real-time compute efficiency, then here the situation is pretty good. These solvers that I described, when the system model is linear, then they maintain some property known as convexity, and that means that they can run really fast, and that's good for us. In terms of robustness to misidentification, then I'm kind of arguing that the situation here is somewhere in between, because there are methods for robust control with linear models that improve the robustness, but they typically come at the expense of performance. So in some sense, roughly speaking, the more robust you want to be, then the less effective your control moves will be if your model is accurate. Yeah, so the situation is somewhere in between there. Moving on to kind of the next step with MPCs, and that is an MPC with basic nonlinearities. What do I mean by that? This refers to an MPC where the system model includes basic nonlinearities, things like quadratics or other simple functions. Okay, so now the CVs in the next time step are some function that's nonlinear. They depend on the CVs, MVs, and DVs in the current time step through some basic nonlinear function that has parameters. What's an example of a basic nonlinear function? For example, it could be a quadratic. Okay, so the CV in the next time step could maybe be a quadratic. In the MV, where the coefficients of the quadratic, theta 1, theta 2, and theta 3, are parameters of the function. This is something that has been explored in the industry, and it is included in modern APC packages. Many of them, at least, that do include different sorts of nonlinear models. And in terms of the success criteria, then I'm arguing here that, again, the ability to capture complex systems is limited because you can only capture basic nonlinearities. And usually real-world systems are not quadratics or things like that. The dependencies are very complicated. And so there's a limitation to how far you can go in terms of capturing a real-world system with such basic nonlinearities. In terms of real-time compute efficiency, the situation here is kind of somewhere in between. The solvers now are non-convex, and roughly speaking, the more nonlinear the function is, the less efficient the solver will be. So if the function is very simple, very close to linear, it'll be more efficient. If it's less similar to a linear function, the solver will be less efficient. You're somewhere in between there. And in terms of robustness to misidentification, then the situation is roughly similar to before. You can promote robustness, but it will come at the expense of performance. All right, let's now move on to the third type of MPC that we see, and that is MPC with scheduled parameters. Here, we have an MPC of one of the previous types, could be linear or something with basic nonlinearities. And now the parameters of the model, whether it be the gain matrices in a linear model or the parameters theta in a basic nonlinear model, these can change over time. They can follow a schedule. Okay, so the system and the surroundings deliver their status to some kind of schedule, and that schedule determines the parameters for the system model. Okay. How is the schedule determined? So it could be defined through various processes. You could come up with a schedule based on step testing, based on first principles and domain knowledge, or based on machine learning, even using neural networks. Right? And the use of machine learning and neural networks for gain scheduling is something that's known in the industry as hybrid approaches. Some refer to it that way. And this gain scheduling has been explored in the industry. In fact, gain scheduling with step testing and with first principles has been used for a long time, quite extensively. Gain scheduling with machine learning and specifically with neural networks is something that's a little bit newer, but it is something that modern APC packages, at least some of them, do include. Now let's talk about the success criteria with this type of MPC. The ability to capture complex systems, here I'm arguing that it's kind of somewhere in between. You can capture steady state nonlinearities through the schedule. Okay? That schedule could adapt the gains. If I'm not defining how the schedule works, then it could do so arbitrarily. Okay? So it could represent different gains for different situations, but the dynamic optimization, that takes place once the parameters are set, that is either linear or nonlinear with basic nonlinearities. So you can capture complex steady state behavior, but you can't capture complex dynamical behavior. In terms of the real-time compute efficiency, then the situation is exactly like it was before, because running the schedule is typically very, very quick. And then the solver will be the same as it was before. you got the parameters from the schedule, and you're just dealing with a linear or a basic nonlinear MPC. And with robustness to misidentification, the situation is also similar to what it was before, because you can basically, at a given point in time, when you run the solver, you are facing a linear MPC or a basic nonlinear MPC, and you can apply the same robustness methods like you could before, and they will take the same toll in terms of performance, the quality of the control moves, like they did before. Okay, let's move on to the fourth and last type of MPC that we'll talk about, and that is MPC with foundation neural networks. Okay? And that refers to neural networks which are large. It's typically at least tens of millions of parameters, and they are end-to-end. Okay? So your entire function that you are trying to represent, to build the entire model, is just based on a neural network. You drive the input to the neural network, and it produces the output. Okay? These models are state-of-the-art in learning from data. We talked about this in previous parts. This is both in practice, right? All the modern image recognition, speech recognition, text analysis, text generation, all these generative AI models, they're all based on foundation neural networks. And this is also something that is backed by mathematical theories. I was fortunate to take part in the development of some of these theories. That's what I got the Google Fellowship for. And I'm obviously not going to get into the details of these theories, but I will mention that one of the main results is that foundation neural networks have universal capacity, which basically means they can represent any function given sufficient depth and sufficient width. Okay, so now let's talk about foundation neural networks in the context of MPC. Okay. I will mention just a note beforehand is that these models, as we discussed previously, they can be guided by first principles. Okay, so your foundation neural network can include in its training, in its learning, first principles like mass balance, volume swell, and different empirical relationships and other examples. And this is something that Immubit has a patent pending for. And using foundation neural networks that are guided by first principles, you don't have to build a full-blown first principles model. You can only introduce the first principles of which you are certain, and therefore you can avoid making unrealistic assumptions. And that is typically a problem with going about it in the other direction and building a model from first principles, making a lot of assumptions, many of which might not be fully accurate, and then including some component in there that's going to be learned. Okay? They're both combinations of learning and first principles, but one of them is a data first approach and the other is a first principles first approach. And the data first approach allows you to make a lot less assumptions and basically only introduce first principles that you are certain of. So in complex settings, which are difficult to model through first principles, this approach is often advantageous. And now let's finally get to MPC with a foundation neural network. Here, your system model is a foundation neural network. Okay? It's just an MPC with the system model being a foundation neural network. This is something that Immubit has patented. It is, to my knowledge, not very common in the industry. And actually at Immubit, even though it's patented, we do not use it for real-time control and optimization. It's used for offline analysis. And the reasons why it is not used for real-time control and optimization will be described right now when we talk about the success criteria. Okay? So we have 3 success criteria. Let's go through them one by one. The ability to capture a complex system is definitely there. Because foundation neural networks have universal capacity, then they can represent essentially any system if they are large enough and wide enough. In terms of the real-time compute efficiency, then here it is a problem, because running a solver over a foundation neural network is typically very computationally intensive. It's not something that you can do every few minutes, let alone every few seconds. So this is a significant problem. And in terms of robustness to misidentification, then this is also a significant problem, because solvers over foundation neural networks are very sensitive to the identified parameters. What do I mean by that? I mean that if the parameters of the system model, which in this case is a foundation neural networks, are not perfectly tuned, and they never are, then the solver will be misled by these inaccuracies, and it could lead to control moves that are entirely off. Okay? And I would like to now demonstrate this. Okay, so I'll show a couple of videos here, both pertaining to the classic example that I described at the beginning, an FCC. Okay, so I just would like to remind, we have the heavy feed rate, the total feed rate, and the riser temperature. These are the MVs. There are a number of CVs. A critical one is the olefins rate. It's on the top right. And there's the objective function, which is an economic objective. Now, let me explain what we see here. This is a video of results obtained with a linear MPC. I'm only showing a linear MPC, but we got similar results with MPC that has basic nonlinearities, and also when the parameters are scheduled. And what you see here are the three MVs on the top row. On the bottom left, you have the olefins rate. That's a CV, a controlled variable. And on the bottom right, you have the objective function. Okay? And you can see the upper and lower bounds of the three MVs where they are set. And you can see the upper bound of the CV, of the olefins rate. You can see them all. There are many other CVs and DVs that I'm not showing just for simplicity of presentation. In black here, that represents the optimal trajectory. That's the optimal MV moves, okay, and the resulting behavior of the olefins rate and of the objective function. Okay, that's what you have in black. This is a simulative environment, so we could actually compute what the optimal moves are. And in blue, that's the trajectory of a linear MPC. That's the moves made by a linear MPC and the resulting olefins rate and the objective function. The horizon here, that's kind of the horizontal axis for each plot, is a few hours. And what I'm going to do now is run the video, and every frame of the video will correspond to a different upper bound for the olefins rate. So I'm going to increase the upper bound, and you are going to see how that impacts the optimal trajectory and the linear MPC trajectory. Okay, so every frame in this video shows you the entire horizon. And what I want you to notice is how the optimal moves behave. And I want you to look, as they change, how the linear MPC behaves. And you're going to see that the linear MPC follows a certain trend, and then at some point kind of flips direction and goes in the other trend. And the optimal moves, on the other hand, are much more balanced. So let's play this. I'll do it a couple of times. Okay, so you can see the optimal moves, how they change, and they're kind of floating. The linear MPC is still following the first trend, and then at some point it flips. Okay, so look at the riser temperature. That's the rightmost MV, for example. Goes down, goes down, goes down. And then at some point, it starts going up. That's very characteristic of linear MPC. They either take the MVs this way or that way. And you can see, looking at the CV, the olefins rate at the bottom left, and on the objective function, that the objective with linear MPC is suboptimal. It's lower. Or the olefins rate is being violated. That's what you see at the end. Okay, so let me play it one last time. Yep, it flips direction and then starts violating the CV bounds. Now let's move on to MPC with a foundation neural network. And what I want you to see here is how the trajectory of the neural network MPC, how it fluctuates, how unstable it is. Okay, so you can see how the optimal moves change, and you can see that the MPC over the foundation neural network just kind of jumps. It's very unstable, very sensitive to local inaccuracies. So in many cases, the objective is suboptimal. In other cases, the CV bound is being violated. It's very characteristic. That's the lack of robustness going on here. Okay. And now let's move on to talk about reinforcement learning. In reinforcement learning, we are tackling the process control and optimization problem that we saw before. And now our controller, instead of being implemented with a solver, it's just a function, okay? Pi of phi. Okay? It's a parametric function. The MVs at the current time step are set by a function, pi, and that function depends on the CVs, the DVs, the objective parameters, and the constraint parameters. And that function has parameters, okay? It's a parametric function, phi, and these parameters, phi, are set through experience, meaning through trial and error. So I basically run the controller and tell myself, okay, the performance was what it was, and what I'm going to do now is try and change the parameters phi, the parameters of the controller, so that the performance is a little bit better. And then I try out different things, and I change it again and again and again, and choose the parameters that give me good performance. So I basically learn through trial and error. Okay, that's the idea behind reinforcement learning. This is an approach that's very successful in other domains that allows doing things that are impossible. Were impossible until they were achieved. Okay, so some examples that we described are beating the world champion at Go and autonomous driving. Something that I did not mention is that reinforcement learning is actually also an essential component of generative AI models. It's not the main component there, but it is something that's critical for getting the highest performance. Okay? And in all of these applications, they are all based on foundation neural networks. Okay, so in the process industries, when we want to control and optimize a plant, then trial and error over that plant, over that true system, is oftentimes too dangerous, too costly. We talked about that. And a solution to this could be, to run trial and error over a system model. Okay, so we have the control and optimization problem, and instead of running over the system, we run trial and error over a system model. Okay. So how does this look? How does the training of the controller look? Every scenario, every trial and error iteration looks as follows. I take objective parameters and constraints parameters, and I randomize them. Then I take the CVs at some point in history, the DVs at some point in history, and the DVs over following points in history, following time steps until a predetermined horizon elapses. These are all taken from historical data. Then I feed the CVs and DVs in the first time step into a system model. And I also feed them into my controller, which also receives the objective and constraints parameters. And that controller drives the MVs at the current time step. And then the system model produces the CVs in the next time step. And they're sent into another instance of the system model, which also receives the DVs in the next time step. And the CVs and DVs in the next time step are sent to the controller, which again observes the objective and constraint parameters and drives the MVs in the time step that follows. And then the system model gives me the CVs in the time step that follows, And I continue that way till the last instance of the system model and the controller. And I have the objective function, which depends on the MVs, CVs, and DVs throughout the horizon and on the objective parameters. And I have the constraints evaluation, which depends on the MVs, CVs, and DVs throughout the horizon and on constraints parameters. After each scenario, what I just described as a single scenario, after each scenario, I adjust the controller parameters, phi. I adjust them, I move them a little bit in order to maximize the objective while respecting the constraints. Okay, so in every scenario, I adjust the parameters a little bit, and then I run another scenario and another one, potentially millions or tens of millions or hundreds of millions of times. And that way my controller learns through experience, and it sees a lot of different scenarios. How does the real-time control and optimization, how does it look like? At every time step, I have my controller, I have my system, I have the surroundings, and I have the users, the domain experts, the operators, and the engineers. The users determine the objective parameters and the constraints parameters. The system produces the CVs, the surroundings produce the DVs, and the controller produces the MVs, and that's it. After another time step, this happens again and again and again. So it's very simple, very efficient. You just run the controller once. Notice that there is no system model in this scheme. The system model is not used in real-time control and optimization. That's a very big difference from MPC, where the entire essence of real-time control and optimization is to run a solver using the system model. Here, the system model is only included implicitly in the experience gained by the controller. All right, so now we have model-based RL, and we can combine it with foundation neural networks. Okay? We can implement model-based RL with a foundation neural network system model and a foundation neural network controller. And this is actually ImuBit's first and most fundamental patent. This is something that is emerging in the industry. There are more and more companies in various spaces, started from refining, but now it's used far beyond that in cement and other verticals. And this is what underlies ImuBit's optimizing brain. And so we like to explain our technology through the analogy to optimizing brain and having very kind of intuitive and illustrative ways to present it. But from a technical perspective, this is what goes on there. It is model-based RL with foundation neural networks. Okay, so how does the implementation process look like? You start by learning a model of the system, which is a foundation neural networks. This could be from weeks to months to years of historical data. Then you take that system model and you train on top of it a controller, which is also a foundation neural network. This is based on reinforcement learning, on trial and error, millions or tens or hundreds of millions of scenarios that are used to gain experience that's equivalent to tens of thousands of years or more in human time. All of this happens offline in the cloud. Then the controller is taken and applied to the real system for real-time control and optimization in closed loop. Now let's talk about the success criteria that we saw before. So the ability to capture a complex system is there because you have a foundation neural network. It has universal capacity. The real-time compute efficiency is there because all you're doing in real time is every step you're just running a foundation neural network once. Even though that foundation neural network is very large, running it once is something that can easily be done in a few seconds, okay, or even less. And in terms of robustness to misidentification, this actually leads to much more robust control. And this is a very kind of delicate and profound point. because the control moves are made based on experience gained over millions or tens or hundreds of millions of scenarios, local inaccuracies of the model under these particular conditions do not necessarily mislead the controller, because the controller has not only seen these conditions, it's seen other conditions as well that could be similar to this one but different. So the errors, in some sense, average out. There's an implicit, robust control mechanism going on here, and I would like to demonstrate this with the videos. Okay, so we have our FCC example. This is linear MPC. We already saw this. I'm just reminding of the behavior that kind of trends in one direction and then abruptly switches to the other direction. That's linear MPC. Then you have MPC over a foundation neural network with these instabilities. And now let's move to RL. Okay. Again, you can see here the exact same scheme. It's the MVs on the top, the elephant's rate on the bottom left, objective on the bottom right. Black is the optimal moves. Blue is what the RL controller produced, and this is at the beginning of training, at the very beginning. Okay. And what you can see here is that basically the RL controller doesn't really respond to the elephant's rate, to the elephant's bound changing. It barely trained. It doesn't have any experience at all, essentially. It's like a baby operator, if you will. This is in the middle of training, after a few hundreds, I think, iterations. And you can see here that the controller does adapt to the bound. It does change its moves, but it's still pretty suboptimal. And this is at the end of training. This is after a few million iterations. And what you can see here is that the control moves they're not optimal, but they're pretty close to it. Far better than with the other methods. Let me play it again. It's much closer to optimum. Okay, so is everything rosy and are all of our problems solved? No, it is. There are some caveats, and it is important to mention one of the central ones, and that is that now the real-time control and optimization is very efficient, but the training is something that's very compute intensive. Those millions or tens of millions or hundreds of millions of scenarios, running them is very, very expensive. Okay? And even though it's done offline in the cloud on huge data centers, if you want to be able to train in a reasonable time, which typically is on the order of overnight, then that will limit the size of the problem that you can tackle. And by size, I mean things like the number of variables, number of MVs, CVs, parameters, number of constraints. And so even though it's done on the cloud, and even though it's offline, it still is a limitation. Right? However, the cloud compute is something that constantly grows. And that means that without doing anything, just by virtue of the cloud compute, larger problems become more and more feasible. And the problems that are being solved today with this approach are far larger than ones that were feasible a few years ago. Additionally, it is possible to solve large problems today by breaking them down into a hierarchy of controllers, and that way you develop controllers for portions of the plant, and there's a supervisory layer on top that orchestrates them. This is something that Immubit has a patent pending for. And now let's conclude. So starting with a recap, standard model predictive control is typically linear, or it has basic nonlinearities or scheduled parameters, and the capacity to capture complex systems is limited. You could capture local behaviors of complex systems, but global behaviors, it's very, very difficult. Foundation neural networks have universal capacity, and they can be guided by first principles without making unrealistic assumptions. Model predictive control with foundation neural networks is something that's not robust to misidentification. We saw those instabilities. I demonstrated them in the video. And reinforcement learning with foundation neural networks is robust to misidentification because of the implicit robust control gained through the experience, through the millions or tens or hundreds of millions of different scenarios. And it leads to state-of-the-art performance in various domains. And now just a concluding word, perspective, that's actually not exactly mine. I'm plagiarizing it, but if I'm doing so, it might as well be from Albert Einstein. And what he says is that information is not knowledge. The only source of knowledge is experience. You need experience to gain wisdom. So I'm not sure what concrete example Einstein had in mind when he said this, but the way I interpret this saying is as follows. Having information about the world is not enough to make decisions. You can't use your knowledge about the world and try to run mental what-if analyses and determine your conduct that way. It's just doomed to fail because your information of the world is always going to be partial and it's never going to be perfectly accurate. On the other hand, if you have experience and you've seen different conditions, they're never going to be identical to the current ones that you're facing, but they're close. Then you gain this intuition that allows you to make effective decisions. And to me, that exactly distills the difference between model predictive control and reinforcement learning, between acting based directly on a model and gaining experience. And that is the reason why I believe that reinforcement learning will become a more and more central piece of the solution to process control and optimization. And with that, I'll conclude.
Thank you, Nadav. We've got about 10 minutes to take some questions from the audience, and I see a bunch of people have found use of our questions and console, so I'll go ahead and run through some of those. And if we don't have time to answer your questions live, Nadav or a member of our team will follow up with you directly via email following the webinar. So let's get started with one around the source of data for your demos that you showed here. Specifically, this is the source of the data for the linear MPC demo. Is it from a real unit with real MPC, or is it simulated data? Same question applies for the foundation neural network MPC data.
Yeah, so it's not a real system, it's simulated. It's basically a simulator that was built using historical data and parameter tuning, domain knowledge, and then you run based on that.
Thanks. How do you define the optimal trajectory for the MPC video?
So because it's a simulator and because you have basically unlimited time to search for those optimal trajectories, there are methods that you can run to, it's basically a solver over the simulator. It's very inefficient, but you can run it.
Got it. Next question is kind of more towards the guardrails around the RL-based system. Are there tools that are being used to ensure that the model is not applied outside of the operating conditions under which it was trained? And then are there tools being used to retrain the model to cover the new operating envelope online?
Yeah. So first of all, if we're talking about it, ImuBit's product, it includes a lot of aspects that I didn't talk about at all today. And one of them is a software layer that sits on top of or has priority over anything the controller wants to do. And the user can perfectly define the conditions under which the controller is allowed to move and not move. And there are always there's an operating envelope, and always the controller is the kind of software takes over when the conditions go beyond the envelope. In addition, there's a confidence mechanism that even if it's within the envelope, the controller can say that it's not confident about the current conditions, like they were not sufficiently represented in the training data. Right? So that's something that also, even if the software doesn't take over, that's something that also is being used. In terms of automatic training, then you get recommendations for training, but right now, as a kind of pragmatic product decision, there is no automatic training that the user isn't aware of. The user always has to initiate the training by themselves. But they do get kind of indications that this could be beneficial.
Along that same thread, would it be feasible to override a control strategy between MPC and the RL controller?
Override a control strategy between MPC? Does that mean
That's the
like
way.
merge?
So that's the way the question's phrased. I'm not
Okay,
totally clear if we're
so
talking about
so so
just
let
shutting
me.
it off or anything.
Okay, so I guess if we could interpret the question in different ways, I guess I'll just choose to interpret it in one way, and I'll say if the question is around combining model predictive control and reinforcement learning or things like that, then there will be more to come on that soon. It's kind of a teaser.
This is like a
I use
practical
the
question.
opportunity. Yeah.
Practical question for software implementation. So when you're implementing the RL controller in the plant, how does it communicate with the manipulated variables? Is it directly through the PLC?
So there is a software layer that we have, and it writes to the DCS typically.
DCS or external targets to APC, right? In cases where
Yeah,
there's
it's
an
also
existing APC
could
layer.
be so some it's about half of the implementations at present are on top of APC, and usually the mode of integration is by writing to the targets, the MPC, and sometimes it's directly to PIDs. Usually, if the customer already has APC in place, we recommend leaving it in. And maybe somewhat ironically, the added value when APC is already there is greater usually than the added value when it's not, because usually these sites are better maintained and are kind of ripe for optimization. So kind of if you have APC in place, the added value you will get is actually usually higher, but it's not necessary.
Expanding on that question, what DCS and PLC systems can you implement this new RL-based software on top of, and how do you recommend going about updating the equation? I'm not sure exactly what we're talking about with regards to the equation, but
Okay, so
I think we could start
I
with
bet,
just general like DCS PLC systems,
yeah.
and if you don't have a strong answer, we can take that as well.
Yeah, so on the integration side, I guess the best people to answer that question would be our kind of system integration engineers, and that can be taken offline. I will say that it's completely agnostic, the solution and the algorithms to that layer of the software, the integration. What was the second? What was the
Second
second
part of
part
the
of the question?
question was a bit confusing, so we'll let that one go offline as well. So let's take one more question online and then wrap for the day. And this one is about data quality ahead of
Yeah.
going into the model. So how about sensor validation before you use a value as an input to the model? Are you
Yeah.
using auto-associative neural networks to check the quality of the inputs to the model?
Great question. So in our platform, this is also something that I didn't talk about at all, but I do think we have some product webinars and venues where it'll be discussed more. So there's an entire platform, Immubit's industrial AI optimization platform, and a significant part of the platform is the building of models. And there's a plethora of tools there to assist in the phases of cleaning the data, choosing the data, and configuring the controller. And there's a lot of machine learning going on for this kind of assistance. This is, in the literature, it's called AutoML. It's machine learning for automating and expediting machine learning development. There's a lot of technology around that I did not get into at all, because it's more of kind of on the periphery of MUBIT's technology. But it is something that's critical. And actually today, most of our efforts are on directions such as this.
Thanks,
It's less
Nadav. And
around
if
a
you
core
would,
algorithm and more around the AutoML, the explainability, interpretability. Yeah, sorry.
awesome. If you wouldn't mind toggling to the next slide, I just want to close out today with a reminder that
Oops.
the full webinar series is available on demand at this point now. So I threw the link in the chat as well. You're welcome to view any of the episodes that Nadav presented over the last 3 months from this same webpage. And we thank you all for joining us today and wish you a great rest of your day or evening.
Thank you very
Thank you
much.
all.